As the first quantum mechanical example, and the simplest in a way, I'm going to consider this ammonia molecule. This is NH3 ammonia. Why I'm giving this example? Because the symmetry group is actually quite easy to see that it is D3 dihedral group, right? The symmetry group is D3, and so as a result we would like to see, for example, the implications of that symmetry group in the energy levels. I want this to be a very simple problem, so as a result I'm not going to make the problem complicated. So as a result I'm going to disregard the nitrogen atom at the center, so just forget about it. I'm just going to consider the hydrogen atoms in here, but I can make it a little bit, I don't know, more general. Let's just consider, for example, somehow three atoms, sorry about that, three atoms. There's a molecule formed from three atoms. Let's say it like this. This is X3. I don't know what X is, but somehow only the 1s orbitals coming from these three atoms somehow is relevant. So as a result, let's say it like this, only single s orbital from each atom is relevant for valence orbitals. For valence orbitals of the molecule. All right, let's say it like this. In the ammonia, of course, we have orbitals coming from the nitrogen, the 2s and 2p orbitals, and the 1s orbitals coming from the hydrogen. And there is this hybridization in here. In any case, we have just a linear combination of the 1s orbital of the hydrogen and the two orbitals, 2s and 2p orbitals of the nitrogen, will basically form this covalent bonds. But I mean, since this involves more number of orbitals coming from the nitrogen, it makes the problem a little bit more higher dimensional and more complicated. So what I do is I just take a single 1s orbital from the hydrogen atom, or think of it as a problem like this, an arbitrary X3 molecule where an s orbital is contributed from each atom. So the valence orbitals that are basically the most significant orbitals of the electrons are basically formed as a linear combinations of these three. So I'm going to call them as phi 1, phi 2, phi 3. Right? These are essentially orbitals that I have drawn like these, phi 1, phi 2, phi 3. Okay, I'm going to assume that they don't have any overlap. Right? Assume that phi I, phi j is equal to 0 if I is different than j. Do I need to assume that? No, it's not necessary, but it just makes the problem a little bit more complicated mathematically. So I'm also going to assume that they are normalized. So therefore, this phi 1, phi 2, phi 3 is an orthonormal set. Orthonormal. It's not an orthonormal basis, of course, but it's just a set of orthonormal functions, because there are some other functions as well in this infinite dimensional Hilbert space of wave functions for electrons. What else? So we would like to then compute the energy level. So since we have three orbitals, we are going to compute, we are going to find that there are three energy levels, and we would like to see what we can say about these, right? So for this I'm going to construct a Hamiltonian, of course. So there's this Hamiltonian in here. So that's going to be a 3 by 3 matrix. So by just looking at the symmetry, I mean, this is not something that you have to do in here, because I'm just going to I'm going to derive the representations later on. But you can kind of say that, for example, all the diagonal entries in here are equal, because epsilon 0 is essentially the expectation value of the actual Hamiltonian, this is the differential operator, if you remember, in the ith state. And it doesn't matter whether I choose the orbital on this atom or on this atom or on the other one. By symmetry, of course, they should give us all the same numerical value in here. So this is by symmetry, but probably without using group theory, it's wrong for me to actually state this in here, but that's something that you can easily understand. So these are called on-site energies. And then there are these off-diagonal terms in here, like that. What are these? They can be zero. They can also be non-zero. Usually they are non-zero. So I'm going to call, for example, phi I h, phi j. These are usually called Tij. These are called hopping terms. Why do we call them as hopping terms? Because it's something like this. If I place an electron in one of the atoms only and not the other one, so you just place the atom on the first orbital, for example. In that case, of course, with time, the wave function is going to change. So together with these terms, with the help of these terms, this electron is going to hop to the neighboring terms. And so as a result, in this time-dependent scenario, these terms are responsible for this hopping phenomenon, the moving phenomenon. So some people also make it think that these are actually the equivalents of the kinetic energy. So these are the terms that prevent the electron from staying on a single site. Okay. So as a result, in here we have the hopping terms and the on-site energies. By symmetry, these are also equal to each other. So all of these off-diagonal terms are the same. They are real because the orbital is an s orbital. Reality is a different kind of an issue. That's also a symmetry requirement. But in here, using the symmetry, you can also show that these off-diagonal, all of these off-diagonal terms are also exactly equal. I'm going to show them actually, but I need these representation matrices. All right. So, and the question is, of course, what are the eigenvalues of eigenvalues? We would like to solve them. This is also another of those problems that to be able to solve the eigenvalues, you don't need to know any group theory at all. It's just a very simple 3x3 matrix. You can also notice that this epsilon 0, they are just appearing on the diagonals, and they appear on every diagonal. So it's like that. I'm sorry about this. Let me just write it mathematically like this. So therefore, I can think of this as epsilon 0 times identity plus t times this matrix in here. Okay, t times that matrix. So as a result, the only important relevant part in here are the eigenvalues of that part, and to those eigenvalues I'm just adding epsilon 0. So you're going to find that you're going to find that all of the eigenvalues actually contain an epsilon 0 in it and plus t times something else in it, right? We are going to discover that that's going to be the form. Epsilon 0 just shifts all the energies by some certain amount. So it's just there. This is usually negative, of course, so that all of the orbital energies are negative because somehow when you leave the electron there, it cannot escape to infinity. Okay, so what's the group theoretical point of view? So we have a group. Group is, the symmetric group is D3. So you can think of it like this. We have some kind of a mirror plane in here. This is a plane, and since the molecule is three-dimensional, I couldn't draw the plane. So there is a mirror plane in here. So when we are mirroring these, this 2 and 3 are exchanged. So therefore their orbitals are exchanged. What else? There are these mirror planes as well. I couldn't draw them symmetrically, so just imagine them to be symmetrical. There are these three operations in here. And what else? There are these rotations as well. So as a result, what we have is a threefold rotation axis in here at the center. So there's a threefold rotation axis, and there are these mirror planes. So that means there are 6 operations in there, and the group is basically dihedral group. We know that this is isomorphic to S3, because I can also consider these operations as the permutations of these atoms with each other. With the s orbitals, everything is very simple. So what we are going to do, so we know the representations of S3, for example. And so as a result, I'm going to use the same representations, but I'm essentially talking about D3 in here. All right, so what else? This is the group, but we have, from the group, of course, we obtain some, I'm sorry, let me just not use hat in here, some matrices. So let me say it like this. The group has some kind of rotations in it, including the reflections. So for each rotation, I have a matrix which basically corresponds to the changes that happen in the orbitals when this takes place. Right? Let's just say it like this. And so therefore this AR is a representation of R in dihedral group. So A is a representation of D3. A is a function of from the group to the 3x3 matrices. And what I want is basically the characters of A. What are the characters? Again, there are these 3 conjugacy classes. So for each conjugacy class, I need to find the character. So from the characters, we can decompose A into, let me write it down like that. We can decompose the representation A into its irreducible representations. And from here, we are going to say something more. But let's say something about these representation matrices. So I'm going to talk about these operations. So one of them is this R is identity, in which case A of R is also identity. The corresponding character corresponding to identity is equal to 3, obviously. That's the simplest case. Let's consider the case where R is a threefold rotation. Right, that's a 120-degree rotation actually, so it just rotates like that. And R inverse is just the inverse of that, right? So that means this rotation maps 1 into 2 and 2 into 3. So you can see that the corresponding rotation operator in the Hilbert space takes the 1s orbital that's located on the first atom and maps it to the 1s orbital to the second atom, right? Please keep in mind that this is an s orbital. If I rotated it around the center on this atom in here, in that case the wave function would not change. But I'm not rotating around this atom. I'm rotating around the center of this molecule, and this rotation carries the atom to the second atom. So therefore it also changes the wave function. So this equation would look like, in our case, is that A of R applied on the first wave function gives me the second wave function. All right, that's basically what it means. So how can I read this? This basically says that in A of R, just keep in mind that this is the first standard basis vector. So A of R applied on the first standard basis vector actually gives us the first column of that matrix. So the first column of this matrix is 0, 1, 0. By using this, we can actually find the first column. And then, well, we just continue. So this rotation applied on phi 2 is going to give us phi 3. Applied on phi 3 gives us phi 1. So from here we can then compute the second column and the third column in here. So let me quickly fill these things out. 1, 0, 1, 1, 0, 0. This appears to be a permutation. But of course, it's just a coincidence. Just keep in mind that these are s orbitals. If I used p orbitals, for example, probably we will have signed numbers in here. Depends on which p orbitals are we talking about. Okay, so just keep this in mind. So the p orbitals, I think I'm going to solve the same problem together with the p orbitals, but in that case the representation matrices will be different, and the decomposition of the representations in terms of the irreducible representations would also be different. Okay, so in any case, why do I need to do this? Well, I don't need to do. So the character of that R is therefore equal to 0 because the diagonal entries in here are all 0. In principle, if the rotation changes the atom in the molecule to a different atom, then the diagonal entry coming from that orbital or those orbitals belonging to those atoms will be 0. Since this threefold rotation just moves every atom to somewhere else, the diagonal entries are equal to 0. Okay, so let's then pass to the reflection symmetries. So there's a mirror plane. Let me call this as x. This operation as x. I don't need to know what this thing is. I don't need to know the matrix form of that operation, right? I just need to know how this thing acts. So I know that this corresponding rotation operator applied on phi 1, this is the first atom, gives me phi 1. Applied on phi 2 gives me phi 3. And applied on phi 3 gives me phi 2. Because this operation just exchanges the second and the third atoms. Therefore, it moves the s orbital of the second atom to the third and moves the s orbital of the third atom to the second. But somehow it fixes the s orbital of the first atom. Let me erase everything in here. So, in any case, so this implies that A of R is it's a 3 by 3 matrix. I'm going to read the first column of A of R from this first equation in here. So that's basically 1, 0, 0. I'm going to read the second column. Second column is for this one should correspond to the third wave function, third orbital. So its column vector is 0, 0, 1. 0, 0, 1 is the wave function for the third orbital in a way, but in the matrix form, and so on, right? You just do it like that. So again, for these, the diagonal entries are equal to 0 because the atoms are exchanged. So the only diagonal, non-zero diagonal entry is the first one. So therefore, the corresponding, I call this as x. Let me correct this. I should have called this as x. In any case, this character is equal to 1. So let's remember the character table of D3. So we have identity in here. We have reflections. We have what? We have 120 degree rotations. There are two rotations. They have different matrices, of course, but they have the same character. So let's remember these. So U1, U2, U3. These are 1, 1, and 2 dimensional. U1 is the trivial representation. U2 is the representation which has signs 1, minus 1, and 1. Just remember that this corresponded to the signature representation of the permutation group S3. And the third one has this, I think, let me check this. So we have one element in here, 3 elements from reflections, and 2 rotations. Let's see. These 2 rows should be orthogonal to each other. What I do is, let's say it like this. I am multiplying each entry of that row with each entry of this one, and then multiplying with the number of elements within the class, and their sum should be equal to 0. We see that 2, 1, 1, we get 2. We get 0 from here, and then minus 1, 1, 2, we get again 2, minus 2, and they add up to 0. Right, so these are irreducible representations. And then at the bottom I also draw the write down the characters of A. So identity has a representation, the character which is 1, which is equal to the dimension. Reflections, the character was 1, and rotations, the character was 0. You can see that this is just the sum of these two. So therefore A is a direct sum of U1 plus U3. What is more, A is unitary, because this is actually coming from the fact that this dr is unitary. It's norm preserving, so any kind of a norm preserving transformation is unitary, right? So what does that imply? This implies that the invariant subspaces of A corresponding to U1 representation is orthogonal to the invariant subspace corresponding to the U3 representation. So that means if I find this subspace, I would have also found this subspace too. Okay, but one of them is one-dimensional. So this is the complex three-dimensional vector space. I'm just going to draw it like that. There's a one-dimensional subspace in here, and all the vectors in here, there's just a single one actually, transform like a U1 representation. And let me, I don't know how to call this, but I can picture it like that. So as a result, this complex vector transforms like U1. Let me erase this. The vectors in here, in this two-dimensional subspace, they transform like U3. U3 is of course two-dimensional, so therefore the corresponding subspace is two-dimensional. So I can easily see that, I mean, this subspace corresponds to the vector 1, 1, 1. I just need to normalize it. Let me call this 1 over root 3. 1 over root 3. So I'm going to call this as, let's say U1. I don't know. So I then need to find a basis for this subspace. In that case, I'm going to define U2 and U3 as two vectors which are actually orthogonal to the first one. So as a result, I'm going to choose 1, minus 1, 0, and 1 over root something, 1, 1, minus 2, and the square root of 6, I think. So these are going to be a basis for the other subspace. Okay. There are, as I said, there are some systematic procedures for finding these subspaces or finding these vectors, but I'm not going to go into these. But you may want to read about these from elsewhere. These are actually you can define some projection operators by using the transformation matrices. All right, so let's then come back. So that means, I mean, since each representation appears only once, U1 appears only once, U3 appears only once. We are in a lucky situation. We don't need to diagonalize anything. So this picture basically tells me that this U1 is an eigenvector of the Hamiltonian. So it has an eigenvalue epsilon 1. I don't know if it is ordered like that, but I don't know whether this is the correct order, so I'm not going to say anything about this. But U2 and U3, they are also the eigenvectors. Epsilon 2 U2. And HU3 is equal to epsilon 3 U3. But epsilon 2 is equal to epsilon 3. These two are degenerate. And that's why I just chose these randomly. So it doesn't matter whether the vector is U2 or U3 or any linear combinations of these two. We are going to get the same eigenvalue. Why we did get same eigenvalues in here? I made the discussion before, so as a result I'm not going to repeat it in here, but this actually follows from the fact that the Schur lemmas, they actually follow from the Schur lemmas, and so therefore we just have this degeneracy in there. So what do we do then? So the result is actually very simple. So we know the Hamiltonian, that's the matrix. I mean, we should have computed this, and also we have also verified that these entries are the same. So you just need to do these. I'm sorry about this. I didn't write down the symmetry statement. So first, let me just do this. So the symmetry statement. It's basically the statement that A of R multiplied with the Hamiltonian and inverse of A of R multiplied with the Hamiltonian gives us the same Hamiltonian. So for all R in the group, symmetry group. So that's the symmetry statement. We usually sometimes write it down like that, not usually, because this is kind of easier to see. It basically tells us that if I do a rotation, then the Hamiltonian describing my system doesn't change. How do I see this? Because if I rotate this molecule, the molecule itself doesn't change. We just change the atoms' places, but the potential that's seen by all the electrons, they don't change. So when we usually do the transformation of the Hamiltonian, you do a similarity transformation like that, right? But I'm not going to show the detailed arguments in there. But instead of this, people usually use this commutativity argument. So you just need to move this inverse to the other side. When you do that, the statement basically reduces to this. That the Hamiltonian commutes with the representation matrices. And this is true for all situations where you have symmetry. So if your molecule has symmetry, then your Hamiltonian should commute with all the representation matrices. This is true for the infinite dimensional problem as well. And if you choose your molecular orbitals in a symmetric way, this is also true for the submatrices as well. All right, sorry about this. I should have actually told you about this earlier. In any case, by using this or this form, you can really verify that these entries are equal to each other. But I'm going to leave that to you. You just need to use, I don't know, you may need to find some of the other representation matrices corresponding to other mirrors as well, probably. But you just need to try it. In any case, so that's the symmetry statement, and from the symmetry statement then we reach to this conclusion that the eigenvector that corresponds to that transforms like the U1 representation is also an eigenvector of the Hamiltonian, and also the vectors that correspond to the invariant subspace of the representation that transforms like the U3, they are also the eigenvectors with the same eigenvalue. Right? I'm not going to repeat the argument in here. So what we do is, once we do that, you just apply Hamiltonian to U1 and see what you get. This is very simple in here. So let me quickly do 1 over root 3, 1, 1, 1. You can see that you're just adding these numbers in here. So therefore, this is epsilon 0 plus t, 2t divided by root 3, 1, 1, 1. So from here, you find the first energy eigenvalue to be equal to epsilon 0 plus 2t. Is this the ground state? I don't know. Depends whether depends on if t is positive or not. It can be negative. Right? What else? Then we try U2. H applied on U2. So let me also do this quickly. I'm going to write down 1 over root 2 somewhere else. Let's write it down like that. So that normalization is irrelevant. I'm just trying to identify the eigenvalue in here. So you can see that in here, at least first entry is epsilon 0 minus t. And what you get is this. Just do this calculation. Just find all the entries, and you're going to find that this is indeed the case, that the eigenvalue is that. So as a result, the second and the third eigenvalues is equal to epsilon 0 minus t. All right, so therefore, that's the solution of the problem. We have found all the energy eigenvalues and the energy eigenvectors. So as a result, that's the end of the solution. But let me just say one more thing in here. The sum of the eigenvalues, the epsilon 1 plus epsilon 2 plus epsilon 3, is also equal to the trace of the Hamiltonian, because the trace of a matrix is always equal to the sum of the eigenvalues. So as a result, I mean, since we know that the trace is 3 epsilon 0, once I have found epsilon 1 in here, I didn't need to do the second computation in here, because from the trace rule, that was the only possibility. That's something that you can see. Okay, so that's one comment in here. So sometimes you may do these kind of shortcuts in the solution of your problems. So that's one comment. Second comment, I have talked about this thing before. Epsilon 0 just shifts the all of the energies by the same amount. So we have also seen this. So that's also another comment. Let's add one more. Let's suppose that the t is negative, right? If t is negative, so in that case, epsilon 1, which is epsilon 0 plus 2t, is the ground state. I'm sorry. And then there are these, the second first excited and second excited levels have the energy of epsilon 0 minus t. So these are the excited states. So these two levels are degenerate. So there's a degeneracy in here. And the degeneracy is twofold. Degenerate. This degeneracy directly comes from the symmetry argument, actually. So it is twofold degenerate. Why twofold? Because the symmetry group has a two-dimensional representation. So as a result, in this system, I mean, if we just make the system a little bit more complicated, but the symmetry group is still D3, we can have non-degenerate levels corresponding to either U1 or U2 representation, or twofold degenerate levels like that corresponds to U3 representation. But you should never see threefold degenerate or fourfold degenerate things without any symmetry reason. So usually in these kind of physical systems, if there is no symmetry, then there should be no accidental degeneracies like that. So all of the degeneracies somehow actually come from some symmetry reason, and the number of levels which are degenerate is equal to the dimension of some irreducible representation of a relevant symmetry group, right? That's one of the things that you should keep in mind. Again, let's just say that there are also real energies. So in that case, the real ground state energy should be less than epsilon 1. And the real second and third excited state energies should be less than or equal to, right? This epsilon 2, which is the same thing as epsilon 3. So as a result, the real levels will be somewhat like that. So the real levels would also have the same symmetry structure, provided that, of course, we have made a good approximation in choosing our molecular orbitals. So as a result, we have a real non-degenerate ground state, and again, real excited levels would be degenerate, because degeneracy is basically coming from the symmetry argument.